video, we're going to discuss electromagnetic waves and how electromagnetic waves or electromagnetic radiation are very similar and very different to mechanical waves. First of all, mechanical waves require a medium. That medium can be air, it can be water, it can be a piece of string, but mechanical waves have to have matter that oscillates. Okay? Electromagnetic waves can travel through a vacuum. In other words, when you have electromagnetic waves, you don't have to have a medium. You can have a medium. Electromagnetic waves will travel through air, they will travel through water, they will travel through what we call optical mediums, things that are transparent quite easily, but they don't need a medium. They're not vibrating the water or vibrating the air to make the wave travel. It brings up a really different idea, and that is really, okay, if they don't require a medium, what's oscillating? I know in a water wave that water molecules are oscillating, right? I know if I have a slinky, the slinky coils are oscillating. But what's actually oscillating when I have an electromagnetic wave? Well, I can draw a picture of one. There's what we usually think of as the y-axis, and here's the x-axis. And this one coming out of the board is usually called the z-axis. We don't use the z-axis a lot, but in a three-dimensional world, we can have an x, a y, and a z-axis. When you have an electromagnetic wave, what's actually oscillating are electric fields and magnetic fields. So if I set up a situation where I have an electric field that's vibrating, it might look something like this. And you'll see that looks like what you think a wave should look like. Electromagnetic waves are a transverse oscillating, and that's our electric field. So I have an oscillating electric field, and then perpendicular to that, we have an oscillating magnetic field. Magnetic fields have the symbol B. We haven't studied that, but it would look something like this. And these would be perpendicular to one another. I don't know if this really looks perpendicular the way I want it to. But what it means is, if my magnetic field is oscillating up and down like this, my magnetic field would be back and forth like this. I always say this is my electromagnetic field hula dance, where one is going up and down and one is going back and forth. So the thing that's oscillating are the fields. Now, we don't go into a lot of electromagnetic theory in this class, but what we do know is that anytime you have an oscillating electric field, it will induce an oscillating magnetic field. And anytime you have an oscillating magnetic field, it will induce an oscillating electric field. So this is basically what we consider a self-propagating wave. Okay? This self-propagating wave is how energy from the sun reaches the planet Earth through a vacuum. We get lots and lots of energy from the sun, and that energy travels through empty space with no matter that's actually waving. Okay. Now, one of the things we know is the way I've drawn them, I hope you can see this, is that the electric field, which is a capital E, is always perpendicular to that magnetic field. They're at right angles with each other, okay? And that's about all I want you to know of what an electromagnetic field looks like. It looks like a transverse wave where you have an electric field and a magnetic field, but they're both oscillating like you would think of a normal wave oscillating. Now, when scientists talk about light, and we talk about light a lot, what they really are usually talking about is the electromagnetic spectrum. And from now on, the word electromagnetic is so long, it'll be a capital E-M. So if I'm talking about the electromagnetic spectrum, what I'm really talking about is all light visible and invisible. Or oftentimes we call this electromagnetic radiation. Of the electromagnetic waves out there, we can only see a tiny, tiny part. That tiny, tiny part we see is called visible light. We know that it's made up of colors: red, orange, yellow, green, blue, violet. Those are the colors of visible light. Most light is not visible. I don't want to get bogged down in all the numbers part, but I'm just going to say way down here, the very longest wavelengths and lowest frequency, longest wavelength, and by longest, I mean as long as 100 meters. We start way down here. That's one end of electromagnetic radiation. And we can come all the way over here to where we get the highest frequency. And the shortest wavelengths. Put the symbol for it. How short am I talking about? I'm talking about something that's 10 to the negative 14 meters. So anywhere from a few hundred meters all the way down to 10 to the negative 14. These are generally considered low energy. These are going to be high energy. Okay. So there is a mnemonic I'm going to tell you in a minute. Let's just write each one of them down. We start with radio and television waves. You know what radio and television waves do. They literally are sent out from the antennas, the broadcast antennas of the radio stations. And if you tune in your dial on your radio, you can hear them. We don't have very much broadcast television still. Most of us now get digital television. But for a long time and during my childhood, you had to have an antenna on top of your roof, adjusted the right way, so that you could tune in and pick up television signals. So radio and television are one type of electromagnetic radiation. Okay? After radio and television, we talk about microwaves. I'm going to run out of room. I'm going to tell you what, I'm going to bunch these together. Radio and television, kind of overlap here. Then microwaves. Well, one of the things we use microwaves for is the obvious thing. We use them for cooking in microwave ovens. But we use microwaves for lots of other things. And one of your favorite ways we use microwaves are cell phones. Your cell phone towers, when you make cell calls and things, they use microwave radiation. So the signal goes from the tower to your phone. That's a microwave signal. Okay. The next type is something called infrared. You may have heard of infrared radiation, but you may not be familiar with what we use it for. First of all, infrared is sensed by people. We can sense infrared radiation. We sense it as heat. If you ever stood by a fire and put your hands out and you feel the heat radiating off the fire, that's infrared radiation. If you've ever seen a pair of night vision goggles so that people can, quote, see in the dark, those goggles are just designed to detect the heat from infrared radiation so they can spot living things that radiate heat like you or an animal. Okay? Infrared is that frequency of light that is just below visible light. So this is a frequency of light just a little bit lower than visible light. Hence we call it infrared. Here we get visible light as our next. And although you may think of visible light being a very large part of the electromagnetic spectrum because it's the part you see, it's actually the very smallest part. If I was to draw this all off in scale, visible light would be a little teeny piece about that big out of all of this. Whereas this might be radio waves, microwaves, infrared, but this is visible light. It's a tiny, tiny little piece, a tiny, small piece. After visible light, we get ultraviolet. Usually it's abbreviated as UV radiation. Notice the word violet. Visible light fits right there in a little teeny spot between infrared and ultraviolet, just below red, just above violet light. UV radiation, I'm sure you've heard of that one. UV radiation is the one that's known for skin cancer. If you spend time outside, and we all do, you may not detect how much UV radiation that you're getting. Too much and you can get an obvious sunburn. But the problem is, it has enough energy to penetrate into the beginning layers of your skin. Oddly enough, radio waves are not likely to do you any harm. And although you shouldn't put a living thing inside of a microwave, you can certainly heat up the water and cook it and do it a lot of harm. Standing outside of the microwave is really very little risk to you. But all of a sudden, what we find is if we move across this table from left to right, we get more and more dangerous types of radiation. So ultraviolet radiation can in fact cause skin cancers. Higher than ultraviolet radiation, we have X-rays. X-rays, of course, have a lot of practical uses, like looking for broken bones or studying fossils. However, they present even more danger to human beings than ultraviolet. There's really two reasons. One, they have more energy. Two, as the wavelength is getting smaller and smaller, and it's vibrating faster and faster, a radio wave will not fit inside a cell. It's huge. But an X-ray will. And even higher than that are gamma rays. If you went home and you told your parents you got a huge dose of radiation today, or if you told your friends, anybody, they might be really concerned. Because when we hear the word radiation, this is what we think about. Gamma rays are electromagnetic waves that are a result of a nuclear reaction. These are the ones that cause cancers, like leukemia. Well, X-rays can too. But when there's, the atomic bomb was dropped, all the cancers and things that were related to it. Well, these have tiny, tiny little wavelengths, so small that they can get inside of a cell and do serious damage to the genetic information of those cells, okay? So can x-rays. That's why when you go to the dentist and they want to x-ray your teeth, they'll put a lead apron over you. They want to protect your thyroid gland. They want to protect your ovaries. Anything that they think would carry important, that could be damaged by x-rays, they want to protect. Okay, so this is generally considered the order of the electromagnetic spectrum. Every time you walk outside or stand in a room, you're getting bombarded with electromagnetic radiation. Some of it's pretty harmless. Visible light, harmless. Infrared, that's heat. Obviously, you don't want to burn yourself, but we need heat. If it wasn't for the sun's heat, we'd die. Microwaves, radio and television waves. These seem to be fairly safe, and some of it absolutely necessary. But when we go this way, ultraviolet rays, sometimes we call that black light. It has that purple kind of look if you have UV radiation. X-rays, gamma rays, those can cause real harm to human beings, so really try to avoid those. How are we going to remember that order? We're going to remember it with a mnemonic device, and our mnemonic device is red Martians invented very unusual X games. There may be something else out there somewhere, but this is a mnemonic device that one of my classes and I made up one year. I know everybody thinks Martians are green, but that doesn't work here. So red Martians, radio waves, and microwaves. Radio and TVs generally jump together as one category. Red Martians, invented, that's for infrared. Very, that's our visible light. Unusual, that's our ultraviolet. And X games, X-rays and gamma rays. Your book kind of clumps X-rays and gamma rays together. The gamma rays are the higher frequency of the two. In the same way they kind of lump radio and television together, and we usually do. In terms of wavelength, this is going to be about 750 nanometers way down here. Oh, I'm sorry, that's the wrong thing. Never mind that thought. Okay, so that red Martians invented very unusual X games. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. Lowest frequency, longest wavelength, safest for people. Highest frequency, shortest wavelength, highest energy. These are the most dangerous. They're dangerous because they're small enough to fit inside the nucleus of a cell and wreak havoc. Let's talk a tiny bit more about visible light, that tiny little piece of the spectrum. Even though visible light is the narrowest band of the spectrum, the smallest part of it, it's the one we're most interested in because it's the only part of the electromagnetic spectrum that our eyes can see, that the cones and rods inside our retina of our eye can sense. If we put those in order, that's red, orange, yellow, green, blue, and violet. That's the order of the spectrum. Down here, the very longest wavelengths people can see, about 750 nanometers. The very shortest, about 400 nanometers. In terms of frequency, this is on the order of 4 times 10 to the 14th hertz. And by the time you get over here, this is 7.5 times 10 to the 14th hertz. Now, we can do a few problems that we've really already done with other types of waves when we talk about electromagnetic waves. The same basic formulas apply to other waves. One is that the distance equals the velocity times the time. But for electromagnetic radiation, in a vacuum, it travels at c. What is c? Remember c? That's 3 times 10 to the 8th meters per second. All electromagnetic radiation travels at the same speed in a vacuum. Radio waves travel just as fast as microwaves or visible light or X-rays or gamma rays. They all travel in a vacuum at 3 times 10 to the 8th meters per second. The light you can see and the light that you cannot see. Okay? So we can find distance. So for example, how far will a radio wave travel in 1 minute? Well, we need to have our time in seconds because our speed is in meters per second. So we know that that's the same as 60 seconds. So that distance, which would be its speed times time, if I put that in my calculator, I don't even need a calculator. 3 times 60, that's going to be 180 times 10 to the 8th meters. Of course, that's not good scientific notation, or 1.80 times 10 to the 10th meters. So the answer is really far. I'll tell you this much. It takes much, 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 much less than a minute for light to travel to the moon. It takes a few minutes for light to travel to the sun. So if our sun suddenly went out, we wouldn't know about it for a few minutes. But if something happened to the moon, a full moon in the sky, it all of a sudden went flying to pieces or something, we'd see that almost instantly. Light travels so fast. Okay. The other formula that we've used in the past that we like to use with waves is the fact that V equals lambda times F, or that becomes C equals lambda times F. So if, suppose we have a radio station, and a radio station broadcasts at 105.1 megahertz. I know you've seen all of those numbers with radio stations, 99.5, 101.3, KICS, 105.1. What those numbers are telling you is their broadcast frequency. If it's an FM station, it's going to be a broadcast frequency that's in the megahertz. If it's an AM station, it's going to be a broadcast frequency in the kilohertz, maybe 1250 kilohertz. So our local country western station, 105.1 megahertz. The question says, what's the wavelength? If I want to find the wavelength of that ray, I'm going to use this formula. C equals lambda F. We know radio waves travel at 3 times 10 to the 8th meters per second. That equals the wavelength times 105.1 times 10 to the 6th hertz. Mega, you might have to look that up, but it's 10 to the 6th. When I do that, I'm going to have to divide by 105.1. So if I divide by all of this on both sides, of course here they simply cancel out. I get that the wavelength is equal to about 2.9 meters. So the wavelength that they're broadcast, they're about 9 feet long, 3 meter sticks. Okay. You can see how a wave that's 3 meters long probably really doesn't actually do much genetic damage. It doesn't fit inside the nucleus of a cell. Very, very different than when we're at gamma rays and they were T90 on the order of 10 to the negative 15. Okay. That concludes chapter 22 of electromagnetism. It also concludes all of the new content for this year. So once you've watched this video, you're just where you need to review for test 3, make sure your projects, your group's working on your project, and of course get ready for the final.